Here's a function that involves motion in the vertical direction. In general, we can think of these functions as being position functions. We use s to represent the position. It's generally a function of time, so we have s of t is equal to. In this case, it's negative 16.1 t squared plus v sub 0 or v naught times t plus s sub 0 or s naught. The negative 16.1 comes from gravity, and that's in American units or non-metric units. If this was a metric problem, you'd probably see negative 9.8 there instead, but the rest of the function has exactly the same setup to it. Now the v sub 0 and the s sub 0, or v naught and s naught, those are initial velocity and initial position values. So for the problem we're looking at here, we have an object that's thrown downward from the top of a 1,000 foot building with an initial velocity of 10 feet per second. So v sub 0 is going to be negative 10. And we pick up the negative because the object is being thrown downward. We assume down is negative and up is positive. The s sub 0, which is the initial position, is going to be 1,000 feet. That's where the object starts, is at a height of 1,000 feet. So to start this question, we can write that s of t is equal to negative 16.1 t squared minus 10t plus 1,000. Now, if we want to figure out what s of 2 and s of 3 are, we just simply need to plug in. So s of 2 is going to be equal to negative 16.1 t squared minus 10 times t plus 1,000, where we replace t with a 2 everywhere. So I'm going to pull up my calculator here and give that a shot. I have negative 16.1, and I'm going to multiply that by 2 squared, and then I'm going to subtract subtract 10 times t, which in this case is 2, and I'm going to add 1,000. And that's going to give me a value of 915.6. That's going to be in feet. We're in English units. That's what the 16.1 tells us. We can also see that we have 1,000 feet. We have 10 feet per second. For the second part, we're going to do the same thing, just simply with s of 3. So we're going to have negative 16.1 times 3 squared. We're going to subtract 10 times 3, and we're going to add 1,000 to that. And we get 825.1 feet. So we're asked to interpret our results. S of 2 is the height of the object after 2 seconds have passed. So it's still at a height of 915.6 feet. It started at 1,000 feet. So it's fallen about 84 to 85 feet in those first 2 seconds. S of 3 is 825.1 feet, and that tells us the height that the object still has remaining to fall, if you will. And we could also look at that as telling us that the object has fallen about 175 feet total since it was thrown downward from the top of the 1,000 foot building. In the second part, we're asked to find the average velocity of the object on the interval from 2 seconds to 3 seconds. Well, that's just simply the slope of a secant line connecting these 2 points on the function. So the average velocity average, if you will, is going to be equal to s of 3 minus s of 2 divided by 3 minus 2. So in other words, we're going to take the difference in the y values. We're going to divide it by the difference in the x values, delta y over delta x. That gives us a slope of a straight line. That gives us our average. So we're going to have 825.1 minus 915.6. We're going to divide that in this case by just simply 1 second. And let's see what we get. If we do that subtraction, 825.1 minus 915.6 is negative 90.5, and that's over 1. So we're just going to end up with negative 90.5 feet per second. So that's an average. At S2, the object's going to have a certain velocity. At S3, it's actually going to have a larger velocity as gravity continues to act on it. At every instant in between S of 2 and S of 3, the velocity is going to be increasing and getting more and more negative. But the average of the velocity across all of the moments in time is exactly negative 90.5. And what's interesting there is there are essentially an infinite number of moments of time within that range. Here's another way in which calculus kind of tames the idea of the infinite. we're really kind of averaging an infinite number of instantaneous velocities to get this average velocity. Now, again, what's kind of interesting here is the fact that there's no calculus involved in this question. This is all algebra. And we're doing some pretty interesting stuff here.